Here's the main idea. And you can see Floyd Mayweather, so he won 50 times and he's lost 0 times. Here on the other side, here on the right, this is Marc Champagne. This is me. Here I am with my glove. And here's my boxing record. I've won 0 and I've lost 0. Now notice, this is pretty incredible. I feel really good about myself. Floyd Mayweather and I, we have the same amount of losses. So who's the champion, Floyd or Mark? Oh, come on, guys, come on. Floyd, all right, well, Floyd's the winner. All right, so what's the one-word question I'm going to say? So anyone who answers Floyd, I agree, that's the correct answer. Floyd is the winner. Why? Al says because he has more wins than Mark. Why might I ask, does he have more wins? Why does he have more wins than me? Al says, because he actually fought, right? He actually fought. How many fights have I been into, like professional boxing fights? I've never actually stepped into the ring. If I've never actually stepped into the ring, the fact that I have 0 losses means absolutely nothing. The situation is very different with Floyd Mayweather. Floyd stepped into the ring 50 times. And when you step into the ring, you're in front of another person who wants to bring you down, who's got gloves and who's also buffed and who's going to punch the crap out of you. Now, the fact that he stepped into the ring, all of a sudden, this becomes a big deal. Okay, cool. So let's put that on a shelf for a moment. And let's look at this other example. That's the example of chess. Here's Vera Menchik. Here's her career record at chess. 78 wins, 1 loss. Here's my record. 206 wins and 0 losses. But here's the thing. Vera Menchik was playing chess, but I was playing Mark chess. Does anyone know what Mark chess is? Mark chess is kind of like chess, only Mark gets to change the rules whenever he starts losing. Okay, so now that you know what Mark chess is, who's the champion, Vera or Mark? The correct answer is Vera is the champion, even if she's got 78 wins and I've got 206. Why is that the correct answer? Because she's playing a game where she can actually lose. When I sit across from someone, anyone, I do not have the possibility of losing. We agree that wins are desirable and losses are undesirable. That's what wins are, and that's what losses are. The fact that I've got a very low undesirable loss means nothing. And the fact that I have a very high desirable win also means absolutely nothing. Because in either case, I have escaped the possibility of defeat. I am not genuinely exposed to the possibility of getting my butt kicked. And now remember why we're doing all of this, right? We want to ask, okay, suppose someone says because science says so, what is science? We're about to read a philosopher of science, one of the most important philosophers of science, Karl Popper, who's going to argue that science is distinguished from other intellectual activities by its readiness to lose, by its openness to the possibility of defeat. And that's what makes it valuable. So when science achieves a result, the result matters because it could have lost. When science achieves a result, it matters because it has to play by a certain rule book that it can't just keep changing. On the other hand, you have other accounts of what there is out there and how we know it that have much higher track records than science, but those records mean absolutely nothing because they're always going to turn out right because they're not actually opening themselves to the possibility of defeat. That's the main idea for our reading, my friend. So us humans, naturally, psychologically, like we want to see our beliefs confirmed everywhere. That's what we hate being shown wrong. So if you think about us psychologically, it bothers us to lose. Losing sucks. So we always want to win. But you know what? If you have a belief that never risks being genuinely defeated, then the fact that it wins means absolutely nothing because it's not actually opening itself up to the possibility. So you have lots of beliefs right now. And of course you believe your beliefs. Otherwise you wouldn't believe them. But did you actually ever take the time to put them in the ring? Did they ever compete against an opposite belief? Did you ever expose them to the pressure of competition with a genuine possibility that they might be revised? If you haven't done that, the fact that they're winning all the time and you believe those beliefs means absolutely nothing. All right, so here's our reading, my friends. And as usual, I'm going to put on my audiobook voice, and you've got it all cleaned up, pre-edited, even with some underlining. So enjoy this wonderful piece. Let me give you a report on my own work in the philosophy of science. Since I first began to grapple with the problem, when should a theory be ranked as scientific? Or is there a criterion for the scientific character or status of a theory? The problem which troubled me at the time was neither when is a theory true, nor when is a theory acceptable. My problem was different. I wished to distinguish between science and pseudoscience, knowing very well that science often errs, that is, make errors, and that pseudoscience may happen to stumble on the truth. I knew, of course, the most widely accepted answer to my problem, that science is distinguished by its empirical method, proceeding from observation and experiment. But this did not satisfy me. On the contrary, I often formulated my problem as one of distinguishing between a genuinely empirical method and a non-empirical or even pseudo-empirical method. That is to say, a method which, although it appeals to observation and experiment, nevertheless does not come up to scientific standards. The latter method may be exemplified by astrology, with its stupendous mass of empirical evidence based on observation, on horoscopes, and on biographies. So empirical means based on observation. And guess what? Astrology is based on observation, but it's not scientific. But as it was not the example of astrology which led me to my problem, I should perhaps briefly describe the atmosphere in which my problem arose and the examples by which it was stimulated. Among the theories which interested me, Einstein's theory of relativity was no doubt by far the most important. The three others were Marx's theory of history, Freud's psychoanalysis, and Alfred Adler's so-called individual psychology. There was a lot of popular nonsense talked about these theories, and especially about relativity, as still happens even today. But I was fortunate in those who introduced me to the study of this theory. We all, the small circle of students to which I belong, were thrilled with the results of Eddington's eclipse observations, which in 1919 brought the first important confirmation of Einstein's theory of gravitation. It was a great experience for us, and one which had a lasting influence on my intellectual development. The three other theories I have mentioned were also widely discussed among students at the time. I myself happened to come into personal contact with Alfred Adler, and even to cooperate with him in his social work among the children and young people in the working class districts of Vienna, where he had established social guidance clinics. It was the summer of 1919 that it began to feel more and more dissatisfied with these three theories: the Marxist theory of history, psychoanalysis, and individual psychology. And I began to feel dubious about their claims to scientific status. My problem perhaps first took the simple form: what is wrong with Marxism, psychoanalysis, and individual psychology? Why are they so different from physical theories, from Newton's theory, and especially from the theory of relativity? To make this contrast clear, I should explain that few of us at the time would have said that we believed in the truth of Einstein's theory of gravitation. This shows that it was not my doubting the truth of those three other theories which bothered me, but something else. Yet neither was it that I merely felt mathematical physics to be more exact than the sociological or psychological type of theory. Thus, what worried me was neither the problem of truth, at that stage at least, nor the problem of exactness or measurability. It was rather that I felt that these other three theories, though posing as science, had in fact more in common with primitive myths than with science, that they resembled astrology rather than astronomy. I found that those of my friends who were admirers of Marx, Freud, and Adler were impressed by a number of points common to these theories, and especially by their apparent explanatory power. These theories appeared to be able to explain practically everything that happened within the fields to which they referred. The study of any of them seemed to have the effect of an intellectual conversion or revelation. Open your eyes to a new truth hidden from those not yet initiated. Once your eyes were thus opened, you saw confirmed instances everywhere. The world was full of verifications of the theory. Whatever happened always confirmed it. Thus, its truth appeared manifest, and unbelievers were clearly people who did not want to see the manifest truth, who refused to see it either because it was against their class interest or because of their repressions, which were still unanalyzed and crying aloud for treatment. The most characteristic element in this situation seemed to me the incessant stream of confirmations, of observations which verified the theories in question, and this point was constantly emphasized by their adherents. A Marxist could not open a newspaper without finding on every page confirming evidence for his interpretation of history, not only in the news, but also in its presentation, which revealed the class bias of the paper, and especially, of course, what the paper did not say. The Freudian analysts emphasized that their theories were constantly verified by their clinical observations. As for Adler, I was much impressed by a personal experience. Once, in 1919, I reported to him a case which to me did not seem to be particularly Adlerian, but which he found no difficulty in analyzing in terms of his theory of inferiority feelings, although he had not even seen the child. Slightly shocked, I asked him how he could be so sure. "Because of my thousand-fold experience," he replied. Whereupon I could not help saying, "And with this new case, I suppose, your experience has become 1,001-fold." What I had in mind was that his previous observations may not have been much sounder than this new one, that each in its turn had been interpreted in the light of previous experience, and at the same time counted as additional confirmation. What, I asked myself, did it confirm? No more than that a case could be interpreted in the light of a theory. But this meant very little, I reflected, since every conceivable case could be interpreted in the light of Adler's theory, or equally Freud's. I may illustrate this by two very different examples of human behavior. That of a man who pushes a child into the water with the intention of drowning it, and that of a man who sacrifices his life in an attempt to save the child. Each of these two cases can be explained with equal ease in Freudian and Adlerian terms. According to Freud, the first man suffered from repression, say of some component of his Oedipus complex, while the second man had achieved sublimation. According to Adler, the first man suffered from feelings of inferiority, producing perhaps the need to prove himself that he dared to commit some crime, and so did the second man, whose need was to prove to himself that he dared to rescue the child. I could not think of any human behavior which could not be interpreted in terms of either theory. It was precisely this fact, that they always fitted, that they were always confirmed, which in the eyes of their admirers constituted the strongest argument in favor of these theories. It began to dawn on me that this apparent strength was in fact their weakness. With Einstein's theory, the situation was strikingly different. Take one typical instance, Einstein's prediction, just then confirmed by the findings of Eddington's expedition. Einstein's gravitational theory had led to the result that light must be attracted by heavy bodies, such as the sun, precisely as material bodies were attracted. As a consequence, it could be calculated that light from a distant fixed star, whose apparent position was close to the sun, would reach the Earth from such a direction that the star would seem to be slightly shifted away from the sun. Or in other words, the stars close to the sun would look as if they had moved a little farther away from the sun and from one another. This is a thing which cannot be normally observed, since such stars are rendered invisible in daytime by the sun's overwhelming brightness. But during an eclipse, it is possible to take photographs of them. If the same constellation is photographed at night, one can measure the distance on the two photographs and check the predicted effect. Now, the impressive thing about this case is the risk involved in a prediction of this kind. If observation shows that the predicted effect is definitely absent, then the theory is simply refuted. The theory is incompatible with certain possible results of observation. In fact, with results which everybody before Einstein would have expected. This is quite different from the situation I have previously described, when it turned out that the theories in question were compatible with the most divergent human behavior, so that it was practically impossible to describe any human behavior that might not be claimed to be a verification of the theories. These considerations led me in the winter of 1919 and 1920 to conclusions which I may now reformulate as follows. 1. It is easy to obtain confirmations or verifications for nearly every theory if we look for confirmations. 2. Confirmations should count only if they are the result of risky predictions. That is to say, if, unenlightened by the theory in question, we should have expected an event which was incompatible with the theory, an event which would have refuted the theory. 3. Every good scientific theory is a prohibition. It forbids certain things to happen. The more a theory forbids, the better it is. 4. A theory which is not refutable by any conceivable event is non-scientific. Irrefutability is not a virtue of a theory, as people often think, but a vice. 5. Every genuine test of a theory is an attempt to falsify it or to refute it. Testability is falsifiability, but there are degrees of testability. Some theories are more testable, more exposed to refutation than others. They take, as it were, greater risks. 6. Confirming evidence should not count except when it is the result of a genuine test of the theory. And this means that it can be presented as a serious but unsuccessful attempt to falsify the theory. 7. Some genuinely testable theories, when found to be false, are still upheld by their admirers. For example, by introducing ad hoc or case-by-case some auxiliary assumption, or by reinterpreting the theory ad hoc or case-by-case in such a way that it escapes refutation. Such a procedure is always possible, but it rescues the theory from refutation only at the price of destroying, or at least lowering, its scientific status. One can sum up all of this by saying that the criterion of the scientific status of a theory is its falsifiability. I may perhaps exemplify this with the help of the various theories so far mentioned. Einstein's theory of gravitation clearly satisfied the criterion of falsifiability. Even if our measuring instruments at the time did not allow us to pronounce on the results of the tests with complete assurance, there was clearly a possibility of refuting the theory. Astrology did not pass the test. Astrologers were greatly impressed and misled by what they believed to be confirming evidence, so much so that they were quite unimpressed by any unfavorable evidence. Moreover, by making their interpretations and prophecies sufficiently vague, they were able to explain away anything that might have been a refutation of the theory had the theory and the prophecies been more precise. In order to escape falsification, they destroyed the testability of their theory. It is a typical soothsayer's trick to predict things so vaguely that the predictions can hardly fail, that they become irrefutable. The Marxist theory of history, in spite of the serious efforts of some of its founders and followers, ultimately adopted this soothsaying practice. In some of its earlier formulations, for example in Marx's analysis of the character of the coming social revolution, their predictions were testable and, in fact, falsified. Yet, instead of accepting the refutations, the followers of Marx reinterpreted both the theory and the evidence in order to make them agree. In this way, they rescued the theory from refutation, but they did so at the price of adopting a device which made it irrefutable. By this stratagem, they destroyed its much advertised claim to scientific status. The two psychoanalytic theories were in a different class. They were simply non-testable, irrefutable. There was no conceivable human behavior which could contradict them. This does not mean that Freud and Adler were not seeing certain things correctly. I personally do not doubt that much of what they say is of considerable importance. But it does mean that those clinical observations, which analysts naively believe confirm their theory, cannot do this any more than the daily confirmations which astrologers find in their practice. And as for Freud's epic of the ego and the superego and the id, no substantially stronger claim to scientific status can be made for it than for Homer's collected stories from Olympus. Thus, the problem which I tried to solve was the problem of drawing a line, as well as this can be done, between the statements or systems of statements of the empirical sciences and all other statements. Years later, I called this first problem of mine the problem of demarcation. The criterion of falsifiability is a solution to this problem of demarcation, for it says that statements or systems of statements, in order to be ranked as scientific, must be capable of conflicting with possible or conceivable observations. Now, when we say that a claim is falsifiable, we have to be really careful. A claim can be falsifiable even if we have no clue how to bring about the situation that would show it wrong, or even if we know how to make the situation happen, but we cannot actually perform the required experiment. So for instance, notice this word falsifiable. It doesn't mean false. It means able to be shown false. That's what it means. A claim is falsifiable not when it's false, when it's possible to show it false. So falsifiability is the ability to show something wrong. And a claim could be falsifiable even if we have no clue how to bring about the situation that would show it wrong. So let me give you an example. Let's say, for instance, that you ask that there are an even number of stars. You say, for instance, there's an even number of stars in the universe. Right? Suppose I type that out. So that's going to be the claim. I'm going to ask myself whether or not it's falsifiable. There's a finite amount of stars in the universe, right? So if there's a finite amount of stars in the universe, then however that number is, whatever it is at any given time, it's either an odd or an even number. Do we agree? And I don't think any of us will ever be in a position to count all the stars in the universe. But there's a right and a wrong answer to this claim, right? So this claim is either true or it's false. It could be true, in which case there's an even number of stars, and it could be false. So for instance, if I make the claim that there are an even number of stars in the universe, and the number of stars when I count them ends with 7, is the claim true or false? Let's say I've counted all the stars, it ends with 7. Is the claim at the bottom true or false? It would be shown false. If you could count all the stars in the universe, and at the end you ended up with an odd number, like it ends with a 7, right? The claim would be shown false. Now, none of us are ever going to be in a position to go around with a clicker and count all the stars in the universe. There's no way we can position ourselves in any situation where we could determine with any certainty whether or not it's true claim or a false claim. But it's still able to being shown false. Or for instance, imagine even if we know how to make the situation happen, but we cannot actually perform the required experiment. So for instance, let's say same claim, right? There's an even number of grains of sand in the Sahara. Now that's much easier to check than the whole universe. Do you agree? Like I know what I would have to do to check that claim. You'd have to count all the grains in the Sahara, right? We know how to make the situation happen. We know what it would look like, right? So we know how to make the situation happen. Just take all like even, oh my God, take the Surrey campus, for instance, right? There's this many grains of sand on the Surrey campus or whatever. But we can't actually perform the experiment because we're not in a position to have the budget and the time and the resources to do that. But still, if we analyze the claim that I'm making right now, namely that, let's say, there's an odd number or even number of grains of sand on the Surrey campus, we can see that this claim could be potentially shown wrong. So it's able to be shown false. So that's an important nuance. Even if I can't actually show it false, I know that I can imagine a situation where I could, even if I can't actually make that situation happen, right? So the main idea is that to establish falsifiability, we need only describe a situation, even if we cannot actualize that situation. So I only need to sort of explain to you a recipe for testing. So I'd say something like, well, imagine, we put walls across the 4 sides of the Surrey campus. We get a bunch of volunteers and they got little clickers and they're picking up the little crumbs and then they report back and there's someone counting all of those and something like that. There's no way we can actually do that. But the mere fact that we can describe the situation means, hey, it's falsifiable. The claim about odd or even number can be shown wrong. That means then that when you ask the question, that's a crucial question to figure out whether or not a claim is falsifiable, you have to ask yourself, can we describe a situation where the claim would be shown wrong? There are 2 possibilities. Either you can describe such a situation or you cannot. If you can describe a situation where the claim could be shown wrong, then that means that the claim is falsifiable. If you cannot describe any situation where it could be shown wrong, then the claim is unfalsifiable. That's the antonym of falsifiable. And remember what I said about falsifiable. It just means able to be shown wrong. And so unfalsifiable means unable to be shown wrong. It cannot be shown wrong. And according to Popper, what that means is it's no longer scientific. And moreover, you can take a claim that's falsifiable, that is one for which you can describe a situation where it would be shown wrong, and then you can have these sub-distinctions. You can have the claim is falsifiable and has not yet been falsified, or you can have a situation where the claim is falsifiable and has been falsified. And that's going to give you the following possibilities. If you have a claim that's falsifiable and it hasn't been falsified, then you have an established theory, especially if there were numerous attempts to try to falsify it. If you have a claim that's falsifiable and it has been falsified, like we tried to falsify it and we were able to show, hey, that's wrong, that's just flat out wrong, then you have a disproven theory. And on the other hand, if you have a claim that can't even be falsified, you can't even imagine a situation where it could be shown wrong, then what you have is non-science or pseudo-science. And often it tries to look scientific, right? But nevertheless, it's not actually science because it never steps into the ring. There's no condition under which it could lose. It's reinventing, if you will. Either it doesn't step into the ring, or when it does, it reinvents the rules like Mark chess in order to come out on top all the time, which you can totally do, by the way. And most of human activity is actually devoted to that because, again, psychologically, we hate being wrong. But that's not going to get us one bit closer to the truth. All right, so let's apply this now to one of the possibilities. So there's three possibilities. Let's have a look at established theories. And remember, established scientific theories are regarded with a lot of respect. Why are they regarded with a lot of respect? Well, they're regarded with a lot of respect for the same reason that Floyd Mayweather is regarded with a lot of respect. They're falsifiable, and they haven't yet been falsified. That is, they step into the ring, they could lose, and they don't. And the bigger the contender, if you step in the ring with a serious contender and you still don't lose, you still haven't been falsified, then you've got the championship belt around your waist. And by the way, when you're a boxing champion, can you just wear the belt and never accept challenges? What happens, those of you who know boxing, what happens when you're the champion? Can you just run away with the belt? I win, I'm the world champion, and then you fly off to Cuba and never fight again. Can you do that? You have to put your title on the line, as they say. It's like for the belt to matter, you have to fight against opponents that are for real, and then you emerge. It's the same idea. You could be wrong, you still haven't been, and you've been attacking big contenders. Let's look at an example of that. Let's look at the example of Einstein. So if you remember from the reading, Karl Popper mentions here that Einstein's gravitational theory had led to the result that light must be attracted by heavy bodies such as the sun, precisely as material bodies were attracted. As a consequence, it could be calculated that light from a distant fixed star whose apparent position was close to the sun would reach the Earth from such a direction that the star would seem to be slightly shifted away from the sun, or in other words, the stars close to the sun would look as if they move a little away from the sun and from one another. So let me just explain this a little bit, right? Imagine the claim that Einstein made was that very massive objects bend space and thus light rays around them. So in our solar system, what's the most massive object in our solar system? The sun, right? By far, right? So here's the sun. And you can imagine the sun is on the backdrop of space, right? In space, there's lots of stars. So imagine here's a bunch of stars in space. And those are in the background, if you will. And the sun is moving constantly as far as we're concerned because we're moving and it's moving. And eventually, for instance, the sun will move in front. So the sun here, let me just move the sun. It's constantly moving. There's so much light here, right, that's being emitted by the sun that if there's a star that's close to it, so you can imagine if the star, I'm going to put this star in another color. Let me put it purple, right? I've got blue stars and the purple star. The purple star you can't see during the daytime, right? Because the sun is blinding you so much. First of all, you don't see any stars at all during the daytime. And when it's right in front of it, there's no chance for you to see it. It's kind of like if a police officer flashes their flashlight in your face. You can't possibly see because you're blinded by the light. Well, the idea is this, right? According to Einstein, very massive objects bend space and thus the light rays around them. So you have a situation like this. So you can imagine if we have, let's say, the stars over here. So this is our Earth over here. All right, that's our Earth. And we're looking out into the sky and we're seeing the bunch of stars. So the stars that we saw earlier, they're over here, right? According to Einstein's theory of relativity, so his theory of gravitation, the sun is such a big thing that it bends. Notice how it's curving the light here. It bends the light rays. And so we should be seeing the stars differently as a result of the light being bent. So technically, we should be seeing the stars that we normally see, let's say, at place number 1. Imagine that's place number 1. We should be seeing them at place number 2. That's where we should be seeing them as a result of the sun bending them. But as I just said a moment ago, the sun is so blinding that any stars, because the stars emit light as well, any star's light that would be bent by the sun, we can never actually see as a result of the sunlight. But there is one moment when we can see it. When's the one time when we get to block the sun? We don't want any sun. What's the one time of the year when the rare moments when we can block the sun? Just like put a big cardboard in front of the sun. An eclipse. That's right. There are times of the year, very rare ones, right, when the moon happens to be right between us and the sun. And when it does that, even though the moon is much, much smaller, it's also much, much closer. What it does is it essentially blocks out the sun, which is really neat for us, right? So what it does is when there's an eclipse, it blocks out all of the sun. And then what you end up with, it kind of looks like this. And according to Einstein's theory, when the sun's in front of them, we should see them at different locations. And so let's go back to the passage by Popper and continue. As a consequence, it could be calculated that light from a distant fixed star whose apparent position was close to the sun would reach the Earth from such a direction that the star would seem to be slightly shifted away from the sun. Or in other words, that stars close to the sun would look as if they had moved a little away from the sun or from one another. Now, this is a thing which cannot normally be observed since such stars are rendered invisible in daytime by the sun's overwhelming brightness. But during an eclipse, it's possible to take photographs of them. If the same constellation is photographed at night, one can measure the distance on the two photographs and check the predicted effect. Well, remember our question, right? We want to ask ourselves the following. We want to say, can we describe a situation where the claim would be shown wrong? Well, actually, yeah, we can describe a situation where the claim would be shown wrong. So that's the picture you took of the night sky when there was no sun. Then you wait for the sun to come. So here it comes. The sun's going to be, let's say, I'm going to put it right here. Now, according to the theory, the stars really close to the sun should be bent. So the image we see of them should be a little farther away. So if you look here, let me write that with a marker, right? This one over here. Let me do this really well. All right, this one over here, this one over here, this one over here. They're very close to the sun, right? And then you wait for an eclipse. So you wait for your eclipse to come. And then when the moon gets right here, take another picture. And if the stars look different than when they did before the sun was in front, then you can show that Einstein was right. And if the position's exactly the same, then you can show that Einstein was wrong, that his prediction turned out wrong. In 1915, Einstein made the claim that we just saw a moment ago, namely that massive objects bend space and thus light rays around them, or something to that effect. But we had to wait 4 years, so that is 1919, in order for the next eclipse to come. So we were in a position where we could design an experiment to show that Einstein was wrong. So we could think in 1915 of a way of showing that Einstein's been refuted, but we had to wait 4 years for the conditions to actually happen, for the moon to put itself between us and the star, and then we could take the pictures and compare before and after whether or not Einstein was right. And here you have the images of the stars that were taken. So you have the stars over here, right? You can see they've been circled. Here's the eclipse. So that's the moon over here. And you can actually see a solar flare coming out from the side. It's really, really neat. And you can have a comparison if you look really closely between the picture that's taken in the night sky versus the one where the sun is in front. And the star's position is different from where they ought to normally be, right? Without the gravitational effects of the sun bending the light rays. And in fact, if you want to know how good Einstein was, he didn't just predict, I mean, the claim that I put up earlier, he didn't just predict that the massive body would warp the light. He also said by how much. So the farther away you are from the sun, right, the less this effect will be pronounced. The closer you are, the more the effect will be pronounced. He literally had a specific number in mind. Like he was saying, this is by how many you should expect to see the light rays being bent. And so not only was he saying a risky claim in that it was going against ordinary observation and it could easily have been shown wrong. Remember when Popper talks about the degrees of risk, he was doing something super risky by making claims that were precise, not just saying that they would bend, but by how much. What do you think of that? That's just insane. I mean, look over here, right? And literally he was proven right. But he was proven right because he could have been proven wrong. This is about this possibility over here. That's what we just saw. An established theory, like Einstein's theories in physics, they're established. Why? Because they're falsifiable and they haven't yet been falsified, but they've stepped into the ring numerous times and could have been shown wrong, but they weren't shown wrong, and that's why they're established theories. Now let's look at this now. Let's look at this possibility over here. A theory that's a claim that's falsifiable and that has been falsified. So now it's a disproven theory. Here's another possibility now, the possibility of healing touch. So we saw a moment ago, Einstein can be wrong and is right. Now we're going to look at healing touch. Can be wrong and is wrong. So it's falsifiable and falsified. So enjoy this video.
Here, Priestess Jones says she's pulling out someone's negative energy and shaking it away. I'm struck by how similar it is to what's being done right now in mainstream American hospitals. It's called therapeutic touch, and it's practiced in hundreds of medical centers, even during surgery. In Connecticut, Nurse Ann Miner does therapeutic touch on Lisa Brackett to help treat her leukemia.
I just heat coming from your heart center. Do you feel it? Yeah, I do.
The nurse supposedly feels without touching from 3 or 4 inches away. Feels the defective energy pouring out.
I can feel where the energy is balanced and where it's not balanced. I can feel where it's intense. I can feel it's depleted.
Then she says she channels the healing energy of the universe through her hands to you. There's no scientific proof that this works, but the patient says that doesn't matter.
I don't need explanations because I have faith in the process. That's a really wonderful thing when you feel helpless, terrified, when you're given a diagnosis, like I was.
It's hard to argue with satisfied patients. But 2 years ago, a 9-year-old girl in Colorado thought that for her 4th grade science project, she'd put therapeutic touch to the test.
Today I'm going to test you on how well you can feel the human energy field.
Emily Rose's test was simple. She asked practitioners of therapeutic touch to feel the energy from her hand. But first, she had them put their hand through a towel and a piece of cardboard so they couldn't see where her hand was. She didn't ask them to heal anything. She just asked the most basic question.
Tell me which of your hands you think my hand is over.
Left.
Again and again, touch therapists failed the test.
Left.
Amazingly, they kept volunteering to take the test. And even when they failed to do better at picking the correct hand than they would have done flipping a coin, their faith in their skills was not dimmed.
Okay.
This woman gets right only 3 times out of 10.
How do you think the test went?
I think it went very well.
Okay, you got 1 right. Sorry.
So, were they embarrassed?
No, not really. Some thought if you got 4 out of 10 right, they thought you'd pass. And obviously they didn't know their statistics.
We asked more than a dozen therapeutic touch specialists to come here and take your test, and not one would. Does that surprise you?
No.
Why is it?
Lots of people think that I've scared them really good.
Well, not that good. Though Emily's test got publicity, it was published in the prestigious Journal of the American Medical Association. Since then, therapeutic touch is practiced more than ever.
My friends, how'd you like that video? Oh, I can feel a person's energy field. It's like, okay, cool. How do you know? And that's a falsifiable claim, and it has been falsified. So notice here, you can have a situation where it actually has a scientific status, but precisely because of that, it got defeated. It got its butt kicked. It stepped into the ring, and it got its butt kicked by a 9-year-old girl. Another possibility on our kind of conceptual space there. Now we're going to look at another example of flat earth conspiracy theories. This is going to be a situation where the claim is unfalsifiable. So remember mark chess. Remember good old mark chess. I can't lose at mark chess because mark chess is like chess, but whenever the going gets tough, I get to reinvent the rules. We're going to look at a really fun example now. One of the claims attached to this flat earth thing, because if you just said the earth is flat, that'd be one thing. But the flat earth conspiracy says that to keep us ignorant of the flat earth, governments work together to fake the moon landings and continue to cover up this fakery. They also allegedly prevent us from going to the South Pole. So it's illegal, they say, to go to the South Pole. There's this this big conspiracy between all the governments. They're preventing us from accessing that rim, because you can imagine that's another way of testing it. Go to the South Pole. When you hit that ice wall, climb on top and keep walking. See what happens. And in order for this claim, you know, once you put that in the mix, you can't really show that wrong. So for instance, if you say that the moon landings were fake, right, and you provide evidence, we say, here's a picture. What would a flat earth person say when they saw this picture? So you show them this picture. You say, look, it wasn't fake. See, they came back with pictures. What would the flat earth conspiracy theorist reply? Photoshop. What about this? What would the flat earth person say about this picture? And you can look this up online. Also Photoshop. It's fake. It was staged, right? This was done in a studio. You know, okay, and okay, fine. And so you say, what about this? Right? Everyone saw this go out in the sky. Like you could be there. Like people saw this. These things were built. What would they say? That it was fake? Like then so it went up in the sky and what? I mean, and then this, I mean, look at all of the work that went into this. All of this, right? This was all fake. This was all to make you believe, right? This is all to fool you. What about when stuff landed? So this landed from the sky and it had the astronaut in this capsule. What would the flat earth person say about this? Where did it drop from? It was fake. Yeah. It never reached above the layer, you can imagine, right? This was dropped by a helicopter. This was all staged. And so there's no way that you can ever show that a flat earth conspiracy theorist is wrong. Notice if your only claim was that the earth was flat, you'd be in the other category. So let's go back in our three categories here. If all you said was that the earth is flat, right, you'd be over here. Let me go back to my things. You'd be over here. Your claim would be falsifiable and it would be disproven. So if that's what you said, if all you said was the earth is flat, it would be a disproven scientific claim. Disproven scientific claim. But if you claim something like there's a giant international conspiracy and the moon landings were faked and all of this stuff, then that cannot be falsified. That's an instance of marked chess, right? And that's what the Popper was talking about when he was saying ad hoc auxiliary hypotheses. You can keep making stuff up case by case to refuse to change your mind if you wanted. And you can see why, if you're going to say, for instance, that because science says so, that's your answer to why, how do you know? If science is held to this standard, that's a good answer. But science is a thing that's opening itself up to the possibility of defeat. And so what we started with, and you can do this kind of Q&A, right? We can do questions and answer. What is the problem of demarcation? So if you go back to our reading, what's the problem of demarcation? Well, it's the problem of distinguishing science versus non-science. So you can imagine if I were to make a circle here and I include in this circle everything that's scientific, well, everything that's not scientific is on the outside. And you can imagine for any possible claim that you make, is it on the inside or is it on the outside? Is it scientific or not scientific? And you need a criterion for the demarcation between the scientific and the non-scientific. And what's the standard answer to that, right? What's the traditional way of distinguishing science versus non-science? Well, the traditional way, not the one you've learned today, is to say that science is based on observation. That's probably what you were thinking before you took this class. And that's the sort of ordinary common sense understanding. Now, Popper says there's something wrong with this. What's wrong with saying that science is based on observation? Well, Popper says there are many theories rely on observation yet are not scientific. Flat Earth, by the way, is something that relies on observation. You can look at the night sky. It does look like a dome over your head. It really does. Phrenology, that's the study of the bumps on your head. And according to phrenologists, when you study the bumps on your skull, you can tell about a person's personality and so on. Astrology, your horoscopes. You know, astrologers require star charts. They need observation about where the planets are at any given time. Tea leaf reading, they'll tell your future by looking at your tea leaves. There's all sorts of other things that aren't scientific, right? But they rely on observation. So you can't say that's a bad answer, right? Saying that science is based on observation, it's not that bad, but it turns out not to be that great because it includes too many things. If you have this as your criterion for demarcation, right, the demarcation problem, and you say, well, it's a question of whether or not something is based on observation, you're going to put astrology in here, right? Astrology, right, along with astronomy, because guess what? Astrology, A-L, and astronomy, A-N, are both based on observation. And what you want is you want a situation where you can put astronomy inside the circle, and you want to keep astrology on the outside. And what's wrong with astrology? Well, what's wrong is that, astrology is not making a scientific claim. And what does that mean, right? So what, according to Popper, distinguishes scientific claims from non-scientific claims is that scientific claims are falsifiable. They can be shown wrong. Like, how do you show a horoscope wrong? Like, suppose it says today you're going to be lucky and I had a really unlucky day. Does that show that horoscopes are wrong? Like, no one's going to give up their belief in horoscopes just because on one time it didn't actually pan out. They're always going to foreground those times when it confirmed their views, right? So when your horoscope in the newspaper or on your phone tells you something and it worked out, then you're like, oh, clearly it's right. But when it doesn't work out, you don't remember those. And what does it mean to say that a claim is falsifiable? Well, that's a key notion. It means that we can conceive, though maybe not achieve, a situation in which the claim is shown wrong. So the conceive, though maybe not achieve, that was crucial for us, right? So remember, in 1915, we could already conceive a situation where Einstein was shown wrong, but we weren't able to achieve it. We had to wait till 1919. We had to wait 4 years for the eclipse. But still, the moment you can conceive of a situation where the claim can be shown wrong, then it's falsifiable and it counts as scientific. It doesn't mean it's going to be true, because it could be shown wrong. You could walk into the ring and lose. That's a possibility. And we're not scientists, but what should philosophy take away from this account? So philosophers can think about questions like, what is science? That's philosophy of science. But more generally, what should we take away from this account? Well, then in philosophy, you should always state the conditions under which you're prepared to admit that you're wrong. Like, that's what is a rational approach to figuring stuff out. If you have a belief and there's nothing I or anybody else can ever say to make you give up that belief, then yes, you feel confident about that belief, but you only feel confident because you're like me versus Floyd Mayweather or me playing mark chess. You're not actually stepping into the ring. And so that's the takeaway from us as we move forward. Once again, let me check. Any gods in the room? If you're a god, say yes. If you're not, say no. Just want to check. I'm not a god, so I'm going to write no in the chat bar. So there you go, right? I don't think there's any. I checked my class list. They should put a little symbol next to it, right? None of us are gods. That means, how the hell do we know? We could be wrong about lots of stuff. And how do you know? Until you've actually stepped into the ring. And chances are, and you know this sounds stupid, it's very easy to laugh at the flat earth people. Very, very easy. But you know what? A little part of you, it's like a flat earth person. And you're playing mark chess. You're playing Tania chess or Arnav chess or Ramandeep chess or Muskanpri chess. Like, there are some beliefs that you're going to be like, when you don't like what the world is teaching you, you're just going to make stuff up. You're just going to make stuff up, right? Because you don't want to give up that belief. And you can do that if you want. But then you're sacrificing the rational standing of your beliefs, right? They just feel good because they feel good. And if we're actually, we want to get closer to the truth, then the first step to that is to admit that we might be wrong. And to preferably do more than that, to actively explain the conditions under which we're prepared to say, I changed my mind.